Okay, so in the last class, in the last class we were discussing about the okay. In the last class we were discussing about oscillators topic. So in that we have RC phase shift oscillator, and we have seen so what will be the conditions that has to be satisfied, and we came to know that it is going to have a total it has to satisfy 180 degree sorry it has to satisfy total phase shift of 360 degree or 0 degree, and the total loop gain of 1. So for any circuit to get oscillate, so in order to go through that, so we have seen that the feedback network is going to provide the RC phase shift network is going to provide 180 degree phase shift, and along with that the main amplifier is also going to provide internal feedback of 180 degree, so that it is going to provide 360 degree phase shift around the loop. And in order to find out the gain associated with that, so we have seen that we have drawn the corresponding AC equivalent circuit of this amplifier RC phase shift oscillator, and we have obtained that gain corresponding to the amplifier, and we have also found out what should be the feedback gain. So since it is comprises of only the passive components associated with the feedback network, so it is going to not only provide a 180 degree phase shift, so it is going to provide also there will be the amplifier, the amplitude of the output signal of the feedback will be uh, will be reduced in amplitude when with respect to the input to the feedback signal. So feedback network की input expand होते हैं, so when we look at the output, so we will be seeing that the gain or the amplitude of the output of the feedback network will be reduced when compared to the top of input to the feedback network. So in that sense, we can say that the amplitude is that is the reduction in the amplitude when it is being passed to the again back to the amplifier input. So we can say that the feedback network it is going to reduce the gain, reduce the amplitude. That is nothing but it is going to reduce the gain. So by how much the gain is going to be reduced, that is to be seen, and we have to by how much it has to be the amplifier. Okay. Okay. I'll just wait a minute. Okay, so by how much the amplitude of the phase shift it has been reduced, we need to find out, and then we need to we have to check out that so we have to how much the amplitude has been reduced, and correspondingly that much the gain it has to provide in order to provide the amplifier gain. So in order to provide that, RC phase shift is going to provide total amplifier reduction in gain of by a factor of 29. Hence the gain of the RC phase shift oscillator it has to be greater than 29 or equal to 29. So that is the parameter that has to satisfy the loop gain, and hence the circuit is going to oscillate. And we also know that the RC phase shift oscillator is going to work with respect to the frequency of oscillations or the sustained oscillations. It is going to be less than few hundreds kilos of hertz, and hence few hundreds of kilohertz. So what we are going to do is we are going for in order to get a higher frequency of oscillation, we are going for LC oscillator as well as the crystal oscillator. So today we are going to discuss about that. So before that, so we will just see that so LC oscillator as well. So in that LC oscillator, so we have seen the Colpit oscillators in detail explanation about the Colpit oscillator. So we know that the amplifier in the main network is comprising of an transistor. In the feedback network, the NC tank circuit is there. So NC tank circuit is nothing but so inductor as well as the capacitor being a memory energy storage device. So it is going to consider as a tank circuit whenever it is connected in the feedback path. So it is called as a tank circuit, and hence we can see the L and C combination can be considered by can be done by two ways. One is by having those capacitor divider and or inductor, and or inductor divider over the capacitor. So we can have two type of LC tank circuit. So one is called as a Colpit oscillator, and another one is a Hartley oscillator. So in that, so we can say that so the impedance which has been connected Z1 and Z2 will be of same type, and Z2 Z3 will be of will be opposite type. So Z1 and Z2 in both the cases you can see the both are of similar type, and Z3 will be of opposite type. So because of this we are going to say that this LC oscillator can be categorized into two types. One is capacitor divider, which is also called as a Colpit oscillator, and inductor divider, which is also called as a Hartley oscillator. So in this, how much the frequency of oscillation and how the frequency selected parameter. So we can say that when compared to RC phase shift oscillator, the frequency of oscillations, the sustained oscillation which is going to provide by this LC tank circuit will be very high. So it is going to have a very high Q when compared to that of the RC phase shift oscillator. And phase shift of the oscillator. Along with that, we are going to see that in detail what will be the frequency of oscillation. So the feedback network is again it is going to provide 180-degree phase shift. Along with that, internal phase shift 180-degree will be provided by the transistor itself. So total phase shift will be equal to 0. So we can say that there are a component resistor is also associated with that. So that resistor is going to modulate the losses which is going to occur between the inductor loss, as well as it is there are some losses that is going to occur within the form of charge storage. So charge leakage loss that is going to be happening in the case of capacitor, and the inductor is also going to provide some leakage current loss, so that is going to have. So in order to overcome this, you are going to modulate by connecting one resistor which is going to connect between the collector to emitter. So this is about the in Colpit oscillator, and similarly we can also see the Hartley oscillator as well. So wherein which you can see inductor L1 and L2, and capacitor C is being connected in the feedback part. And then some whenever we can see that whenever the frequency of oscillation, or whenever the input frequency of oscillation is at a lower frequency, we can say that these capacitors will be acting as an open circuit, or it is going to have a high impedance. Because of that, only the inductor is going to have, so in the feedback part, so that is going to have. So for that purpose, so we can say that this is going to operate at a higher frequency. Whenever it is going to have an operating frequency is very high, so it is going to provide a feedback, a complete feedback. And the frequency of oscillation for the Colpit oscillator here it has been given. So since it is going to have a capacitor divider, so it is we also know that it will be given with it is going to have a certain sinusoidal oscillation which is going to have omega naught will be equal to 1 by 2 pi square root of L into C. So C is nothing but a capacitor divider over here, C1 C2 divided by C1 plus C2. So that is what it is going to have. So series. So another Hartley oscillator is also there. So that is going to oscillate with the fundamental frequency. It is will be equal to omega naught will be equal to 1 by 2 pi square root of L1 plus L2 into C. So that is how the frequency of oscillation, and we need to see what should be the loop gain. You know, to have a loop gain, so what should be the feedback factor. So the feedback factor, if it is equal to, it is matched to the loop gain, so the gain of the amplifier. So if the feedback factor, so this is considered the feedback factor, means if the feedback factor or the ratio factor of C1 over C2 or L1 over L2, if it is made equal to GM in times of R. So GM times of R means what? So GM is the output, so transconductance, so wherein which the output amplitude is given by GM times of R, that is the output voltage. So if it is made equal to the gain equation, so the feedback factor is made equal to the output, then you can say that the loop gain around the LC oscillator, that is a Colpit or Hartley oscillator, will be equal to 1. So for that we have generalized the AC equivalent circuit of the transistor, wherein which we have neglected two capacitance, C pi as well as the C mu, C R pi as well as the C mu we have neglected, and we have analyzed the circuit. So by considering V pi as the input signal, and the return signal or the feedback signal which is coming to the input side, which is nothing but voltage across the collector. So we equated those two, and we have generalized the expression for the capacitor voltage, and we have obtained the expression, and substitute the complex frequency variable with AC equal to j omega. So when we substitute this one, so we can see there are two parts available. One is real part as well as imaginary part. So imaginary part, if we equate, so you're going to get the oscillation of frequency of oscillation for the Colpit oscillator as given by this one. So omega naught is equal to 1 by square root of L into C1 C2 divided by C1 C2. So by equating this imaginary part, we are going to get this expression. And next is if I am going to equate this real part with the GM times of R. So if I will be getting the feedback factor ratio. Okay, so if I'm going to get if I'm going to equate the capacity divided, so this is the real part of the expression. So wherein which if you are going to equate to this GM times of R, so you will be getting this ratio G C2 by C1, so that will be equal to GM times of R. That gives that. So in order to obtain the loop gain to be equal to 1, so the amplifier gain GM times of R must be equal to the C2 by C1. So that is the feedback factor. So if it is made equal, then you are going to get the sustained oscillation, and the gain loop gain around the circuit will be equal to 1. So with this we have just concluded the LC oscillator type in the previous class. Now we will move to the last topic in the crystal oscillator. So in the crystal oscillator, so you can see this is the crystal symbol. So here, so this is a crystal oscillator. So these crystal oscillators are a special type of oscillator circuit. So these are all this is going to have a very high Q factor. So when compared to that of any type of for LC oscillator or any type of RC phase shift oscillator, if you see the selectivity parameter of the Q of the crystal, so that is going to have a very high. So what is the advantage of a crystal oscillator? So what is the use of this crystal, and how it is going to sustain the oscillation, and how the crystal oscillator is going to work? So in order to understand the operation of the crystal oscillator, so we can see that crystal so some examples I can give. So tourmaline, Rochley salt, as well as quartz will be acting as a crystal. So these crystals will be working with respect to piezoelectric effect. So whenever you can see in this symbol, so this and center with a rectangle symbol, so that will be considered as a crystal. So can be made up of any particle like tourmaline or rochelle salt, or any quartz crystal type of crystal can be kept inside the two electrodes, within which when you apply any voltage across the two electrode potential, that is, this is nothing but one metal plate, and this is also considered as a metal plate. If you are going to apply certain voltage, so this crystal will mechanically, it is going to deform. So it is going to change its shape, and it will starts vibrating with the fundamental frequency. Whenever the input signal to the voltage is matched to this crystal resonant frequency, it is going to it will start vibrating. So this works under the principle of piezoelectric effect. So inverse piezoelectric effect. So first we should understand what is a piezoelectric effect. So piezoelectric effect is nothing but whenever you are applying any voltage between the two terminals. Whenever we have kept a crystal say between the electrodes, and if you are going to apply any voltage between the two terminals or two electrodes, so these crystals will mechanically deform its shape, and it will start vibrating with its own frequency. That frequency will give certain oscillation. So upon applying external voltage, it is going to change its mechanically shape, and it will start vibrating. That vibration, because of the external voltage, is called as piezoelectric effect. So to change its from one phenomenon, electrode phenomenon, to mechanical deformation, so that is nothing but a piezoelectric effect. Inverse piezoelectric effect is whatever we are going to say, that it is opposite to that of this one. So whenever we are going to apply some pressure, on this crystal, so these crystals is going to provide certain voltage across the output terminal. So it is going to provide certain voltage across the output terminal. So whenever it is going to provide an external voltage across the output terminal, so that is nothing but sustained waveforms across the output terminal. So that is called as an inverse piezoelectric effect. So these crystals, so it is going to work with respect to inverse piezoelectric effect. So they mean in that, so upon application of certain pressure, so it is going to provide certain oscillations across the output. So how we are going to get this work? So this is going to provide certain oscillation, and the quality factor is also very good, and these type of crystals is going to be useful to provide some constant oscillation. So that is nothing but what we will say, So you're going to get a sustained oscillation. So whenever you require stability, so for stability of the oscillations or stability of the circuit, so we are going for crystal oscillator rather than LC oscillator or RC phase shift oscillator, because those oscillations, whichever the oscillations which is going to be provided by both will be of a low frequency type, as well as it may drift. So it may drift its oscillation. That means so the oscillations of those RC phase shift oscillator as well as the what do we call, so LC oscillators may drift because of the variations in the components. So component variations, if it is there, so it is also going to change its oscillation. It will drift its oscillation at the same time. So you will be having the it will be not having any certain stability in the sustained oscillation, and which may also change with respect to change in temperature, change in component values. So if you are having any certain change in the component values or sustained change in the temperature, so RC phase shift as well as a low LC tank circuit, and also they will deviate from from its oscillation. That means the frequency of oscillation may deviate because of those components. L and C. So you can see that in the previous circuit as well. So you can see some of the component which is nothing but it is depending upon the 1 by square root of L and C. So if there is any change or if it is any leakage current or leakage of the charge it takes place, so it is going to be directly inversely proportional to the square root of LC, right? So if there is any deviation, then there will be change in the frequency of oscillation. The same thing holds good in the case of RC phase shift oscillator. So if there is any change in the capacitor or resistance value because of the change in the temperature, so you know that resistors and capacitors and all depends upon the temperature. So temperature, if it is varies, so obviously the oscillations is also going to vary. So when you need a stability or when you need a frequency oscillations to be of a uniform type, so it should not deviate from its it should not get fluctuated. So we are going for crystal oscillators. So these crystal oscillators it is going to provide a sustained oscillation. So sustained oscillation, and because of this they are very much used in the telecommunication range of operation. So and when you're going to deviate with the communication network and also in the working place, so we can see telecommunication, there is a communication related equipments. Those are using these crystal oscillators for transmitting of the signal. And the same time, so even the your laptops, mobile phones, and all, so they are going to use for all the circuits. So for any type of electronic circuit, it requires certain oscillation of the frequencies. The oscillators are required. So these oscillators, based upon this only, you are going to check whether how much is the speed of the hertz. So you can see 3 gigahertz frequency. So what do you mean by 3 gigahertz? So to 2 gigahertz frequency, 8 GB RAM. So all those things which we are going to discuss. So that is nothing but it is going to operate with that high amount of speed. So that is what you are going to say. For in order to get that much frequency, and also we are going to have, so what is the for that operation, so for that sustain high frequency of oscillations will be generated by the help of the crystal oscillator itself. So smartphones are low, so you can see that all for any of the circuits, so for any of the type of application, so all will work with respect to clock. So with it clock will be generated by using these oscillators. So 33 megahertz clock, so you will be seeing, so in microcontroller then they will be explaining the crystal oscillator frequency of the microcontroller is 33.33 megahertz, like that they may have told, right? So that same thing. So at the same time 11.0592 megahertz clock frequency will be required for this Atmel Mega 8051 microcontroller, like that they have might have told. So that 11.0592, why that only specific that frequency why they have kept? So because their oscillator, crystal oscillator is developed in a such a way that that is going to provide that much oscillation frequency. So frequency of oscillation provided by that crystal is going to have that much frequency, because based upon that you are going to call it as a, you are going to have a frequency of oscillation for that microcontroller. It is going to develop that much frequency. So so we have seen some of the applications, and this crystal oscillators also is going to have a higher Q when compared to the higher Q. That is a quality factor, so that is going to provide certain maximum oscillation. So it is going to have a higher value of Q, typically in the range of 10,000 to 20,000. 10,000 to 20,000 Q factor will be there. So based upon that, we are going for all these digital IC applications and all. We are going to useful for crystal oscillator itself, and it is going to have frequency generation from tens of hundreds of megahertz to hundreds of gigahertz. Frequency of oscillation that is going to be provided. So this is going to have a higher frequency of oscillation when compared to LC or RC phase shift. So RC phase shift is going to just provide about hundreds of less than hundreds of kilohertz, whereas LC tank circuit is going to provide hundreds of kilohertz to hundreds of megahertz, whereas this is going to provide the frequency of oscillations from hundreds of megahertz to hundreds of gigahertz. So you can see the frequency of oscillation, as well as because of that you are going to have. And when we come to the activities, so physical activities, so it is going, we can say that there are basically there are three types of crystals which are going to be useful. So one is Rochelle salt, another one is tourmaline, Rochelle salt, as well as a quartz. So for tourmaline, tourmaline is there, right? So Rochelle salt. So it is going to provide a higher piezoelectric effect, whereas a mechanical deformation it is going to break up very fast rate. So Rochelle salt, it is going to provide a higher frequency of oscillation, whereas it is going to break up at a very higher frequency. So mechanical stress it is cannot be hold. So it is going to break up at early stage itself. So whereas a tourmaline, it is going to provide a that is what mechanical effect. So that is mechanical deformation will be very less, whereas a high piezoelectric effect. So it is going to have a high piezoelectric effect. So when we are going to have quartz as a crystal, when you are going to use a quartz as a crystal, so when you are going to have a quartz as a crystal parameter, so it is going to have in between the tourmaline as well as the Rochelle salt. So it is not going to have too much mechanical deformation, as well as too much piezoelectric effect. Because of that, you can say these quartz are very suitable for generating oscillations, and hence these quartz crystals are least expensive. So it is very cheap. It is available at a cheap. These crystals, the quartz crystals are available at a lower cost. At the same time, the performance of it is going to have in between them Rochelle salt as well as a tourmaline. So each one will be having the parameters. So how much? So as I told, it is works with respect to inverse piezoelectric effect. So how much the mechanical deformation is going to cause, at the same time how much the piezoelectricity of the particular crystal is going to have. So it is depend upon these two parameters. So among that, so tourmaline as well as the Rochelle salt. So Rochelle salt is going to provide a high piezoelectric effect, whereas less mechanical result. Whereas this tourmaline is going to have a higher mechanical with less piezoelectric effect. So if you come to the quartz, so it is going to provide in between these tourmaline and Rochelle salt. So it is friendly. It is going to have a very it is going to have the cost effective as well as all the digital electronic circuits, and also we are going to use quartz as a basic. So it is going to have because of highly abundant available in the nature. And then, so when we see the corresponding crystal, so corresponding crystal, you can see this is the crystal structure. So piezoelectric effect crystal structure. And if you write the corresponding electrically equivalent crystal, so this is very important. So this topic, so this is the symbol of the crystal, and this is the electrically equivalent circuit configuration of that parallel of the crystal. So which is comprising of RLC circuit. So this is consisting of resistance component, inductor component, as well as some CS is capacitance in series, and CP corresponds to the parallel capacitance. So with this, you can say that so inductor, capacitor in series, and resistance. So these are all considered as a motional capacitance. So motional inductance, motional capacitance is also called as series capacitance as well as a motional resistance. So that is the electrical equivalent. At the same time, so you can see one capacitance denoted as the CP, that is nothing but the capacitance of the parallel plate. So that is depend upon the type of the electrode which has been given. So that for that parallel capacitance will come. So at the same time, so you can see this is the series part wherein you are going to have L, CS and R. So this R will be having a neglect effect on the impedance, or that is going to have reactance when it is considered. So this resistance is going to have a least effect, and we can say that the L and C, the inductor and the capacitance has been connected in parallel as well as series fashion. So because of which you will be having two types of resonance frequencies that we will be having. So one is the series resonance frequency as well as the parallel resonance frequency. Resonance frequency means when you apply certain voltage across the when you apply certain voltage across this one, so it is going to vibrate. So these crystals is going to vibrate with its resonance frequency. So the type of resonance frequency with which it is going to vibrate, it depends upon whether which type of component is going to be used. So whether it is a series resonance or the parallel resonance. So here they have written the characteristics graph for the reactance, crystal reactance. So it is going to see these are the component parameters which are present over here, and we can say this is the crystal reactance, how it is going to vary with respect to the frequency of vibration. So when you see there is when you apply the voltage across here, so it is if it is frequency of application is very less. So you can see this is omega s corresponds to series resonance frequency, omega p corresponds to the parallel resonance frequency, and you can see the as you can see. So whenever you can see the parallel resonance frequency is having very high value, so you can see this is that it is going to reach across infinity only, whereas series resonance frequency is going to have a value which is be very smaller value. So whenever you can see the series resonance as well as parallel resonance, so you can see that is the electrical equivalent circuit. So whenever you apply, so these electrical components is going to correspond to the corresponding series resonance or the parallel resonance. So this series resonance, it is going to be achieved so at a lower frequency range, whereas a parallel resonance is going to achieve at a higher resonance. And during the both series resonance as well as parallel resonance, you can see the reactance is of inductive type. So inductive type. So the major whether it is whenever it is, you can see omega s as well as omega p, that is the resonance during the resonance frequency. So the reactance exhibited by this crystal will be inductive type. So majorly it will be inductive. Apart from parallel resonance as well as a series resonance, so apart from that frequency, you can see this is nothing but frequency of the crystal. So the away from the series resonance during this time, the reactance will be of capacitive type. And apart from that omega p, that is we can see all the capacitance, the reactance will be of capacitive type. Only during the series resonance to the parallel resonance frequency, the crystal reactance is going to have an inductive type. Apart from that, so the crystal reactance will be of capacitive type. So we can see this is the crystal reactance, how it is going to behave. So with respect to electrical equivalent. So this is about the circuit diagram, electrical equivalent. So this is the circuit diagram of the crystal oscillator, and this is the electrical equivalent of the crystal oscillator, and this is the crystal reactance which is going to crystal reactance of the so crystal reactance versus the frequency, and we are going to see the omega s as well as omega p. This is the series as well as the parallel resonance frequency, and from this we are going to see so the impedance. So if you are going to consider this impedance, so z of s, this is a series as well as a parallel resonance frequency. So we can neglect the resistance R, which is going to have the seen in the crystal. So when you are going to have find the crystal impedance parameter. So z of s, which is nothing but 1 over scp. So this is cp is nothing but the parallel shunt capacitance, and shunt capacitance plus 1 over s into L plus 1 over s into 1 over s by cs. So this is to form some the series impedance, and this is nothing but a shunt capacitance. So it's going to have this as the total impedance, and which you can write in the manipulate, and you can write the form in terms of z of s, so which is going to be divided like this. So this is the simplified version of this one. So this is the impedance, and we can say that the series resonance at the series resonance. So you're going to have this value will be dropped, and in the series resonance you're going to have L into CS. So stray capacitance. This is the series capacitance along with the L. So that is going to have the series resonance frequency. Omega series resonance frequency omega s will be given as by 1 by square root of L into CS, whereas parallel resonance frequency omega p will be given as what? So 1 by square root of L into C equivalent. So C equivalent is nothing but Cs into Cp divided by Cs plus Cp. So that is what you are going to get for the parallel resonance frequency. So that is omega p will be equal to 1 over square root of L into Cs into Cp divided by Cs plus Cp. So if you carefully look at these two expressions, so what is the expression you will be getting? So recall the LC tank circuit. So in the LC tank circuit, so fundamental frequency of oscillation of oscillator, that is Hartley oscillator, will be given by what? 1 by square root of L1 plus L2 into Cs, right? So C. So that is the similar to that of this expression is similar to that of Hartley oscillator. And if you consider this omega p, so that is the oscillation frequency. So 1 by square root of L into Cs into Cp divided by Cs plus Cp. So the equation is similar to that of Colpit oscillators. So we can see we can generalize this in the form of Hartley as well as Colpit oscillator. So L in series with Cs corresponds to Hartley oscillator, that is the series resonance frequency, and parallel resonance frequency means Cs and Cp divided by Cs plus Cp into L. So that gives some Colpit oscillator. So capacitor divider will take place. So that is in the case of Colpit, and inductor divider will take place in the series. So that is what you are going to. You can make a correlation between that. So that is about the parallel resonance frequency. And if I substitute the value of complex frequency variable S with the j omega physical frequency, Js is equal to j omega. So you can see this is the impedance parameter. So that is going to happen. So if you substitute in this, so you're going to get the same expression s square. So that is what you're going to get over here. So minus j into 1 by omega cp into omega square minus omega s square. So omega square minus omega p square. That is what you're going to get with impedance in physical for physical frequencies. So impedance for the physical frequencies, you're going to get the expression as 18.8. And then we can see, since Cp is greater than Cs, so you know that Cp, that is the shunt capacitance that is going to occur between the two metal electrode plates. So it will be always very much larger. So capacitance exhibited by the shunt capacitance is very much greater when compared to the motional capacitance which is connected in series Cs. So the two resonance frequencies are very close. So you can see that the Cp is very much greater than Cs. So we are going to have the two resonance frequency omega s as well as omega p, which will be very close. So when you are going to have crystal reactance, so we can see the shape as shown in the figure below. So above, so we can see this is the crystal reactance for omega s as well as omega p, and we can say that we observe that crystal reactance is inductive type. So it is inductive type during the range of omega s to omega p. So that is to the very narrow range of frequency band between omega s and omega p. So that is this during this band. So you can see this is the bandwidth wherein which the crystal is going to exhibit the inductive type of reactance, that is between the omega s and omega p. It is going to have inductive type of crystal reactance. Whereas outside the omega s and outside the omega p, so all the way, so you can see that the crystal reactance is of inductive type. So that is what you are going to see in the inductive type. So that is what it has written. So for a given crystal, the frequency band is well defined, as well as we can see the crystal reactance is inductive type during the very narrow band omega s and omega p. For a given crystal, the frequency band is well defined, and the inductor of the Colpit oscillator. So the now we may use the crystal to replace the inductor of Colpit. So we can say that this is nothing but the frequency band during this is inductor type, and it can be replaced with the Colpit oscillator. The same data in the during the resonance frequency of that inductor. So L with the series with Cs. So that is the is going to have a smaller capacitance. So omega naught will be equal to 1 over square root of L into Cs, that is equal to series resonance. So that is the that is can be compared with the Hartley oscillator as well. So another important oscillator topic, so which is going to be studied in this one is a Pierce oscillator. So you can see this is a Pierce oscillator. So in this Pierce oscillator, you can see this is the inverter circuit. So it is going to have a NMOS as well as PMOS over transistor over here. So in this CMOS, this is can be considered as a CMOS inverter. So in this CMOS inverter, so outside that is the crystal is connected parallel to the inverter amplifier. So this is considered as a, so you can see this is nothing but a inverter. So outside the parallel to the inverter is being connected with the crystal oscillator has been connected parallel to the CMOS inverter, and then you're going to see C1 as well as C2 as an external capacitance which is connected. So this is going to provide a sustained oscillation. So that is called as a this popular configuration is called as a PS oscillator. So in this oscillator, so the RF determines the DC operating point. So we know that RF is nothing but a feedback resistance between the output and input. So you can see this is the input and this is the output. Drain is the output and this is gate is the input. Between that, so you're going to have one feedback resistance that is connected between this. So that is going to provide a high gain voltage threshold points of the CMOS inverter, and resistor R1 together with C1 provides a low phase shifter. So R1 and the C1, so it is going to provide a low frequency type or low pass frequency type of oscillator. So because RC corresponds to low pass type filter, that is going to provide oscillating at the higher harmonic of the crystal frequency. So this is about the PS oscillator. So today's class we have just seen about the crystal oscillator. So this crystal oscillator is going to be having a very high Q, and it can be operated with few hundreds of megahertz to few hundreds of gigahertz, and it is going to have a higher frequency and it is very stable. So it is going to have, why we are going for this crystal oscillator is because of its which is going to provide a very stable with time and temperature. That means so you can, if there is any variation in temperature as well as if there is fluctuation in the components also, it is not going to affect. So it is going to provide a very stable oscillations, and it is going to have a high Q factor, and its corresponding equivalent circuit model is going to comprise of RLC and another capacitance connected in parallel to that of RLC. So this is a crystal circuit and this is a corresponding electrical equivalent crystal value, and this is the reactance how it is going to vary, and also resonance properties are characterized by the inductance which is going to be as a millihenry to few henries. So it's going to have, and a small series capacitance which is going to have CS as well as in the sense of in the range of 0.0005 picofarad, and this is going to have a very small resistance, and this is going to have a few millihenry to henry. So it is going to exhibit, and this parallel capacitance is going to have a very high value. So this is a electrical equivalent circuit, and correspondingly we have seen the impedance how it is going to crystal is going to provide with respect to change in the frequency, as you are going to see this electrical equivalent. So it is going to have a two resonance frequency. One is series resonance and the parallel resonance of the operation. So this parallel as well series resonance, we can see within the series resonance and parallel resonance. So the reactance exhibited by the crystal is of inductive type, and apart from that, it is going to have a capacitive type of impedance it is going to have, and we can see the series as well as parallel resonance. It can correlate with that of a Colpit oscillator as well as the Hartley oscillator. And you, if you substitute the value of the complex frequency variable with its corresponding physical frequencies, we can obtain the frequency of oscillations. And then another oscillator which we are going to consider only just for this one for stable oscillation is the Pierce oscillator, which is nothing but consists of a circuit diagram of oscillator is to have a CMOS inverter amplifier, and crystal oscillator has been connected in parallel to that of CMOS inverter, and C1 and C2 corresponds to the capacitor, and R1 is nothing but output, and RF is nothing but a feedback that is connected between the output and the input of the inverter amplifier. So that the value of R1 and C1 is going to provide a low pass type of network. So with this the module 2 has been completed. So from next class onwards, I'm going to just start with the third module, feedback network. Okay. So any doubt in this oscillator topics? So this is the four major. In that this crystal oscillator, definitely they are going to ask for the exam. So you should draw the crystal oscillator and this corresponding electrical equivalent, and this is the reactance. So these three figures and these two impedance, if you write, and if you tell the what you mean by crystal and how it is going to oscillate, can be used as an oscillator, and with this definitions, if you explain the properly the value of the crystal oscillator, then they are going to give full marks. So this it will be asked for 6 to 8 marks. So crystal oscillators is very important. uh, till lower semesters and all, you have seen the RC phase shift oscillator, Wayne bridge oscillator and all, as well as LC tank circuit and all. So this is the new concept which you have studied in this. So that is the crystal oscillator as well as the PS oscillator. So these two definitely they are going to ask in the final exam, as well as the internals also. So oscillator topic one questions definitely they are going to ask, since it is a end of the topic. So that is for the module 2, this is the end of the topic. So definitely they are going to ask in the final exam about this. Okay. Okay, with this, any doubt is there? So with this, I'll just conclude today's class. So we'll meet you tomorrow with a new topic. That is feedback network, third chapter, third module. Okay, so I'll just start with. I will just give some 10 to 15 quiz questions in the MS Team. I will just upload in that only. So by tomorrow or day after tomorrow, I will just upload that quiz question as well. So kindly attend that one. Okay. So with respect to each module, I will just give course based upon your understanding with respect to that chapters, that modules. It will be useful. Is it clear? So,
Thank you, sir.
okay.
Yes, sir.
Thank you, sir.
Okay, fine, fine. So 46 members
Thank
are
you,
there
sir.
today.
Yes, sir.
Okay,
Thank you, sir.
thank you. Bye.
Thank you, sir.
ಇವತ್ತೇನ್ರೋ ಹಿಂಗೆಲ್ಲ ಥ್ಯಾಂಕ್ ಯು ಅಂತ ಹೇಳಿ ರಿಪ್ಲೈ ಮಾಡ್ತಿದ್ದಾರೆ, ಇಷ್ಟು ದಿವಸ ಒಂದು ದಿವಸನೂ ರಿಪ್ಲೈನೇ ಮಾಡಿಲ್ಲ.